So take a look at the universal law of gravitation. Now, Newton introduced this law almost 400 years ago. So what it says, the any object anywhere in the universe, any two objects, if they have a mass, then any mass object should have to have some sort of interaction force between any other mass. So that's the basic idea of the universal law of gravitation. So which mean now in this particular chapter, we are not interested very small objects. We are interested actually large object. It can be two planets, planet and the sun, or stars, or two stars, or maybe two galaxies, and then so on. It can be any object out there. So we're gonna, since almost all these large objects, the astronomical objects are spherically shaped, we're gonna treat them by considering their center of mass. So which means basically, if this is a large astronomical object, then we can treat this is the center of mass for object number one, this is the center of mass for object number two. Then if I combine draw a line between those two center of mass, along that line there should be interaction force between the objects. So the 1, 2 right here means the force, the gravitational force acting on object number one, this number two represent due to object number two. Object number two create that attraction force. Similarly here, this number two means where the object acting on, number one means where the force is actually coming from. And that force, Newton explained, the force is directly proportional to the masses of the object. Masses larger object, the force going to be much larger. Mass smaller, the force going to be smaller. That's why if we go into like the extremely small masses like electron or something, then the gravitational force almost negligible because mass is too low. And on the other hand, this force is inversely proportional to the radius power 2. That's why all of these forces we generally call the inverse square law, which means the separation is much larger, the force is negligible, the separation is considerably lower, then the force is considerably large. Okay. Then by combining these proportionality, we can put a proportionality constant. Then this force is equal proportionality constant G m1 m2 divided by r to the power 2. Direction of the force always along the radius direction. That can be any direction, x, y, or any other direction. Okay, that r hat represent the unit vector r direction. And when we go closer to the object, it's gonna be always towards the other object. So the force acting on the object number one towards the force object number two, force acting on the object number two towards the object number one. Now these two forces are equal and opposite. So which means the magnitude wise, if 1, 2, magnitude of that force should be equal to the magnitude of force to 1. And magnitude wise the same, but opposite if I consider this as a system, and then sum of all the gravitational force going to be then cancels out. Now, if I draw this as a graph, uh, the gravitational force versus the multiplication product of the masses, then it's going to be linear. The mass getting larger, the force obviously getting larger. And on the other hand, if we draw this as a function of radius or the separation, then the magnitude of the force is going to be very large when the radius is smaller. The magnitude of the force is going to be very small when the radius is larger. When the radius goes to infinity, force approaching zero. And on the other hand, the radius approaching zero, when then the force is actually approaching infinity. Okay, so that's the idea. And this gravitational constant G actually measured very long time ago, almost like many centuries ago, the 1798, by the Cavendish experiment. You can read the information later. And the value of that going to be something like 6.67 times 10 to the negative 11. And the unit should be Newton meter square divided by kilogram to the power 2. Okay. And the important fact of that gravitational constant large G, which is actually the same for anywhere in the universe, including something around the Earth, closer to the Earth's surface, or anywhere in the universe, it's going to be the same number. Okay, that's the important part. Now, this whole chapter is just based on this formula. Okay, let's take a look couple of applications. Now, if we thinking about the Earth has a center of mass here, then we can treat the Earth mass is actually concentrated into that particular point. Then the closer to the Earth's surface every object is, about radius of the Earth further away. Now, if I consider any object right here, let's consider we have object right here, it's small mass m, then that object should have to have some sort of attractive force towards the Earth's center. That's going to be the force acting on the object. Let's consider this is object now. This is going to be, usually we call the force of gravity, but that is the force acting on the object due to the Earth mass. Similarly, the Earth mass is actually also has attractive force towards the object. Now, if I write it down, this force by using the universal law of gravitation, this is going to be G large m small m divided by radius of the Earth to the power 2. Now, if I rewrite this equation this way, then you can see some sort of similarity or the ideas which we using earlier. If I separate Gm and the R square times the M, what we actually observing here, this constant part, you can see large G is a constant, large M is the mass of the Earth, which is a constant, radius of the Earth is a constant, which means around the Earth's surface, we treated this so far as a gravitational constant. That is the number we're using so far, 9.81. Okay, but we will take a look the 9.81, how it is changing in a bit. But the idea is that, which means we generally say there is some sort of field, gravitational field around the Earth's surface, dragging everything towards the Earth, which is actually this number 9.81, which we can calculate by knowing the large G, large M, and the large R. If I plug all numbers together, then I will end up something like close to 9.81. That's the idea. And if you look at the units, I'm going to end up unit is meter per second squared by putting the unit for G, M, and R. So that's why we called around the Earth's surface, there are going to be some sort of field dragging everything towards the Earth's center. So that is not a force, that is a field, because it doesn't have a unit of Newton, it has a unit of meter per second squared. Everything accelerating towards the Earth's center. But if I have a mass, that particular point, then we can multiply that acceleration by the mass, then that mass will experience gravitational force. Okay, so that's the idea. Now, this is small g, now we know that should be equal to gm over r square. All of these values we know the value of g, which is something like 6.67 times 10 to the negative 11 Newton meter square over kilogram to the power 2. And then we know large m, which is the mass of the Earth, 5.98 times 10 to the 24 kilogram. And then we know the radius of the Earth, which is 6.378 times 10 to the 6 meters. If you put all of these parameters together here, then you will get something close to 9.81. That's the idea. Okay, so that's the number we generally call the gravitational acceleration around the Earth's surface. However, this number can change, because obviously you can see G and M cannot change. Those two will remain in constant, but the R right here is the separation between the two masses. We assume we are assuming Earth radius is actually measured from Earth's center to the mass, so which mean it got which means it's going to be from here, this exact point, this exact point, which is the Earth center, to the mass right here. That's the separation, which is the radius of the Earth. However, depending on the position of the mass, this radius parameter can difference. For example, if we consider object is in a high mountain area, then the radius parameter not going to be the Earth radius itself, Earth radius plus something. So which means this small g obviously changing. Not only that changes because of that height difference, it can actually change because of the Earth rotation. Now, Earth rotate around its axis, right? Let's consider this is the Earth axis. If I draw this line right here, so let's consider that is the Earth axis. Earth is actually rotating around this part. Now, if I have the mass right here, small m, that mass is spinning around that axis, but that mass is not separated from that axis. As a result of that, there's no centripetal acceleration acting on the person when the person is at the pole location, point A. But if I bring the person to point B, that person will experience centripetal acceleration towards the center. That's going to be A of C. That A of C, we know we can calculate mass times the V square divided by the radius of the Earth. That V, we can actually calculate. V is equal to pi r divided by the T. T is actually period of the Earth, which is about 24 hours, multiplied by 60 minutes, multiplied by the 60 second, we can find the time in second, which mean we can calculate the centripetal acceleration. Something you will end up something like 0.0033 meter per second squared if you put all the numbers together. So which mean if I write the F equal ma exactly at point B location, that will end up the force downward direction, which is the force of gravity, which should be equal mass times the acceleration of the gravity that we think that always there, and also plus mass times the centripetal acceleration. Now there's two acceleration there, which mean if I plug this F right here, which is gm small m divided by r to the power 2, which is equal to small mg plus small ac, small m cancels out, then you can see the gravitational constant or the gravitational acceleration at point B is equal gm over r square minus the ac. Gm over r square, we know the number is about 9.81 minus the ac is 0.0033 roughly. You will end up something like 9.79 approximately, okay, meter per second squared, which means the rotational effect is actually reducing the gravity on the equator, gravitational effect at the equator location, okay, and then so on. So which means small g is actually not constant, it even changing because of the rotation. And then this gravitational constant, you obviously know now, you know the equation g is equal small g is equal gm over r square, which means if I go into a different place like the planet Mars has a different mass, and then planet Mars has a different radius, then obviously for the gravitational constant for planet Mars, going to be completely different number you can calculate. If you know those values, then if I do the same for maybe let's say Jupiter, then the Jupiter has a different mass, very high mass relative to the Earth, and then Jupiter has a different radius, larger radius relative to the Earth, then I can calculate the Jupiter gravitational constant on Earth's surface without its rotational effect. Then if I consider the rotational effect and everything, then this G value is actually changing much. Now, the main objective of this use of this equation is actually understand beyond the Earth, basically. We're not interested in anything closer to the Earth's surface, because closer to the Earth's surface, we know how to work with by using the basic reduced version of this idea, okay? Now, the one of the important the investigation we can do is actually the satellites. So we know various types of satellites. We know the Hubble Space Telescope, International Space Station, all of those are orbiting around the Earth's surface with a very large radius, so we can actually understand how to actually put an object into orbit or things like that, right? So let's consider I have a satellite is in motion on this orbit. Let's consider this orbit is like about 2 times the Earth radius, 2 times the r of a, that is the small r. Always we measuring from the center of the Earth, which is where we think the mass is concentrated, and to the object. Object has a small mass. Then in this particular situation, let's consider now, if I consider this object right here, that object should have to have force of gravity that we know G is small m large m over radius to the power 2 should be equal to the centripetal acceleration towards this direction, right? Always object is actually now dragging towards the object can stay on that circle only if it has that centripetal acceleration always, right? In this particular case, centripetal force is the gravitational force. We discussed that very in detail, the connection between the centripetal force and some other physical forces earlier chapters, chapter 4, chapter 6, and then so on, chapter 10. And in this particular case, this is going to be equal to the mass times centripetal acceleration. That should be equal tangent velocity squared divided by r. Then this small m cancels out. Tangent velocity, we now know, I can figure out by knowing, for example, rotational period, right? So that's going to be 2 pi r over t. Then if I put everything together here, this is going to be 4 pi. 4 pi is small r square divide by t to the power 2 times the small r. Then the one of the small r cancels out. Then if I rearrange this equation, I can find the relationship between the period of oscillation should be equal 4 pi square divided by gm parentheses radius to the power cube. Then you can see any orbital period to the power 2 should be proportional to the radius of that orbit to the power cube. This is actually called the Kepler's third law. We will take a look at Kepler's third law later in this chapter at the very end, but this is actually the Kepler's third law. That is a proof of Kepler's third law by simply using the Newton universal equation of gravitation, okay, which is a very important equation to understand satellite motion and then calculate those things and then so on. So then there are various type of satellites. There's various names we use. There's like the elliptical satellite, just moving around the Earth on elliptical path. There's geosynchronous satellite. There's a polar satellite. Always it actually going through the cross section, passing through the pole to pole. And then equatorial satellite. Always satellite is passing on top of the equator. And then the geosynchronous satellite. This is a very specific, very unique type of satellite, particularly the equatorial, polar, and the geosynchronous. All of those are very, very important satellites, but the geosynchronous is actually easy to understand. We'll take a look only some of this, not all. So what the interesting part of the geosynchronous satellite is, geosynchronous means the geostation. So which means on top of one particular location. Let's consider this is the USA. Then if I have a satellite right here orbiting on this particular orbit, then that satellite that to be geosynchronous, then should be always on top of a certain point. So which means the period of this satellite should be 24 hours. Around us, the satellite also rotating around the Earth. So to be stay on top of one particular location, the period should be 24 hours. So which means if I know the period, which is 24 hours times 60 times 60 in unit second, I can actually estimate what should be the orbital speed of the satellite, which means simply 2 pi r divide by t. So by using this information, we can actually calculate, for example, what is the orbital radius of the satellite, right? Because now we know period of the satellite to the power 2 is equal 4 pi square. 4 pi square divided by gm times radius cube. If I know the period, I can calculate if I want to have a satellite which to be geosynchronous, how what is the radius of that satellite? I can actually calculate that by using this simple equation which we built earlier, okay, which is technically the Kepler's third law. Now, if I know G and M, 4 pi is a constant, then we know T in this particular case 24 hours, then we can estimate what should be this radius. But remember that radius should be measured relative to the Earth center, okay? So this should be whole equation is actually very useful. Then one of the other important use of this idea is actually the idea of artificial gravity. Can we create the artificial gravity? For example, if I'm in the space station, then the space station generally on continuous free falling, we don't feel the weight at all. We're going to feel the weightless scenario. So because of that, we're going to move around freely, so which is not going to be very useful in terms of space traveling and then so on. So how are we going to create the artificial gravity? We can create it by just rotating the surface of that space station. So how to do that? If I rotate the space station with some omega, then because of that omega, the tangent velocity should be equal r times omega. So this person always going to experience some sort of tangent velocity that is 90-degree angle radius, okay? Now, which mean the always this person going to experience some sort of centripetal force. Which mean when the person experience some sort of centripetal force, mean the person experience the opposite force because of the Newton third law towards the surface. So that reaction force to the centripetal force, if that force is equal to the mg, like we experiencing on the Earth's surface, then this person gonna feel like he's on the Earth's surface. That's it. So the centripetal force is mass times v square over r. Then the mass cancels out. Then we can easily calculate what should be the tangent velocity in this particular case, rg is square root of that. On the other hand, if I know that tangent velocity, we can actually calculate how faster we should rotate this, because we know omega is equal v over r. We can calculate the rotational speed of this particular space station surface. Now, this is a simulation. You can see this red dot is actually a ball. If we stop this simulation, red ball can go everywhere, because there's no gravitational force. But if there's a gravitational force, you can see if I try to bounce the red ball, after it bouncing from the bottom surface, it's going to come back to the same exact location. It's not going anywhere. It does exactly what it's supposed to do on the Earth's surface. Okay, that's the idea. So then one of the other most important thing in this chapter is actually the general idea of potential energy, gravitational potential energy. We discussed that in chapter. But that gravitational potential energy, remember, relative to the Earth's surface, we assume the Earth's surface is the zero potential point, but that is not universally accurate. It accurate only near Earth's surface. Okay, remember that, because that okay to use that equation. If we're talking about near Earth surface scenario, then in such scenario, near Earth surface, that's extremely important. Okay, near Earth surface, then we discuss this very in detail. We assume the Earth surface where the gravitational potential energy is zero. Then you go its distance above, at that particular point we actually know gravitational potential energy is mgh. But this idea of gravitational potential energy zero at near Earth surface is actually not useful if we're talking about two objects very far away each other. So that's the idea. Then we have to first understand where the gravitational potential energy zero point. Now, gravitational potential energy zero point is actually based on gravitational force itself. So if you look at the gravitational force, gmm over r square, that's the gravitational force, which means to have the gravitational potential energy zero point, obviously the gravitational force has to go into zero, then only the work done due to that force can be zero, which means obviously relative to the Earth center. Yeah, let's assume the Earth center is right here. So that's going to be the mass of the Earth concentrated. Then if I consider another small mass, that mass gravitational potential energy can become zero only under one condition, when the radius is actually infinity. So which means whenever the object is at radius infinity location, then only the gravitational potential energy can goes to zero. Any other place, that object has to have some gravitational potential energy, including the Earth's surface right here, because you can see Earth's surface is r distance away relative to the Earth's center, radius larger distance away. There should be some sort of gravitational potential in that particular location too. That's what we try to find it out here. Okay, so to do this, let's consider, now we know potential is just the work done due to force, right? So let's consider we'll start with this point further away, and then we'll move the object very little bit towards the Earth center. Okay, extremely little bit, so we can calculate the work done due to that particular motion. This difference right here, this motion, let's consider is small dr amount. Then we can calculate what is the work done due to that dr amount, which should be dw. Then if I calculate the total work done starting from r infinity location to some point right here relative to the center, let's consider this is r location, is starting from its center, which is the R0 point. Okay. Then if I want to calculate the gravitational potential at this particular point, then I have to do the work done from the infinity all the way to that R location, right? If I know that total work done, that total work done gonna be sum of all the small work done, which means the integral force dot dr. Okay, so that's the idea. Let's do that. The work done gonna be equal integral initially starting is gonna be u dot dr. Now this force we know gmm r squared. Right? Gmm can come out integral infinity to r. This gonna be the force is actually, you can see, always towards this direction, and the delta r also towards that direction. So as a result of that, we will end up yeah. So this is gonna be just simply d the power 2. The angle between is 0 because that's the same direction we are measuring. So then it's going to be cosine 0. So then this going to end up g m m. The limits is going to be 1 over r. Limits going to be infinity. We'll get gmm over r with negative sign. 1 over infinity is actually 0. Now you can see this work done is actually the potential energy. Gravity is the work done itself. How much work done we have to do to bring the object from infinity to that particular point. So which means this is going to be gmm over r, but negative sign. That negative sign is extremely important. What that negative sign is telling you, this point is actually bound to the Earth center. This is actually bound orbit. So the bound mean, if I want to change, if I have object right here, let's say I have a mass m object right here, that particular object has this amount of energy, right? Negative gmm over r, which means if I want to move that object in or out, then I have to apply external energy. That's the idea of bounding. So we generally call the bound orbit. So that extremely important concept in terms of the satellite motion. Let's take a look at the idea here. Now, if I have a satellite on this orbit, now that orbit relative to the Earth center, this is the Earth center where the mass is concentrated. This is the radius r. In this consider, we'll assume this is like twice the Earth radius or something. Then when the object is actually orbiting right here, object always has a tangent velocity v, which is 90 degree angle to the radius. Object has a certain mass, which is like a satellite. And then if I want to calculate total energy of this object, right, total energy of the object going to be the kinetic energy of the orbit plus the potential energy of the orbit. Kinetic energy of the orbit is half small m times v square, obviously. Potential energy of the orbit, we know gmm over small r. Now, this is small v, on the other hand, we know has a direct correlation to the small radius, right? Because we know the force of gravity, which is gmm divided by r to the power 2, is actually the centripetal force m times a of c, m times v square over r. Small m cancels out, then we can easily figure out v square is equal, one of the r cancels out, gm divided by r. Then if I combine this together, I can figure out the total energy of the orbit, which is equal g large m small m divided by r, and then the half here minus g large m small m over r. If you simplify this, you will get negative gm m over 2r, right? So what does that mean? That means this object is actually bound to this orbit. That's what that negative energy means. This is a bound orbit. Bound orbit means this object not gonna go anywhere. It can rotate forever on that orbit. If it is needed to be changed, you have to supply energy externally. Unless otherwise, object will not change its orbit. That's the idea. This is equally valid for this astronomical situation all the way down to the quantum mechanical situation, electron moving around the nucleus. Electron is bound to the nucleus. That's why electron can move around the nucleus almost forever. This is the basic idea which actually Niels Bohr used more than 100 years ago to actually produce the first quantum model. We do those investigation very in detail in physics class. Okay. And then let's take a look couple of other important things related with this chapter. So the one of the other important thing we're going to investigate, which is the escape velocity. Escape velocity means, now let's consider I have object on top of this tower. So we can give the initial velocity horizontally due to the center. I draw this line right here. That will be the Earth radius, right? This will be the mass of the Earth. This will be the small mass of the object. This part we can say the small h. This part right here, the Earth radius, gonna be so large plus this small h. Okay, and then we can apply the 90-degree angle velocity like the horizontal projectile. Then we can project this object. Then we know object should have to initially go usually parabolic path, then come back to the Earth surface. We did this experiment number 5 also. But if I increase this velocity continuously, then at some point, object will end up going into this circular orbit, right? It will not go into the parabolic orbit. It's not going to come back to the Earth's surface. It can go into the circular orbit if the initial velocity is high enough. But if I increase further that initial velocity, object can actually completely goes away from the Earth gravitational attraction. That we call the escape velocity, right? So which mean at some point, at this particular point, this object has certain amount of velocity. Let's assume this h is extremely small relative to the large r. Because of that, we will treat the small r is approximately equal to the large r. Then which mean when object is starting right here, this will be the initial point. Then object kinetic energy v0 to the power 2. Object has a potential energy, which now we know negative g large m small m divided by r. Then that will be the total energy addition of those two. Then if object is completely goes away, if we provide enough potential energy, this object is completely goes away. At some point, completely separate from the Earth attraction. Let's consider that is the final point. At that point, object velocity will assume eventually become zero. Its kinetic energy will reach the zero. Its potential energy also will reach zero because there's no more gravitational attraction. Then in between the traveling, there's no any energy loss. We can apply delta A from initial to final should be zero. This is going to be kinetic final minus kinetic initial plus potential gravity final minus potential gravity initial equals zero. The kinetic final is zero, kinetic initial mv is square, v0 is square divided by r, plus potential gravity is zero, potential energy is initial negative gmm over r equals zero. Now, if I rearrange this one, I can figure out easily equation for v. Small m cancels out. Sorry, this should be number 2. So this is going to be then 2gmm divided by r is square root of that. Now these are going to be the earth radius, right? So this is going to be then 2I is g mass of the earth divided by earth radius is square root of that. That is the v0. Then we know the g parameter, we know the m parameter, earth mass, and then we know the radius. We can calculate what should be the velocity, escape velocity, if I want to kick something completely off from the earth. You can calculate this number. We will do that in the class. This will end up something like 11,000 meter per second. That's going to be extremely large value. Even if you compare that to the speed of the sound, it's going to be like more than about 30 times the sound speed. It's going to be like we usually call sound speed is 1 Mach. This is going to be like 30 Mach speed, almost impossible to achieve on the Earth's surface. That's why when we want to send something onto the moon or something onto the Mars beyond the Earth gravitational attraction, we have to do various different calculation, put it into various different orbit before we actually sending that. Okay, and that's important idea. Then very last concept we will discuss in this chapter is actually the planetary motion, so which is the Kepler laws. So the Keppler laws is actually produce the foundation for understanding of the our planetary system and then beyond. Really, that is why it is considered very basic model to understand the observable astronomy what we observe out there. So the first law is it actually explain all the planetary orbits should be ellipse. So then we have to discuss a little bit about the ellipses. So what is the ellipse? Ellipse is actually some sort of uh, distorted circle. For example, this blue line is actually a circular orbit, right? That's a perfect circle, and the red line is actually an ellipse, right? So which mean what's the difference between them? This is elliptical, uh, elliptical orbit. This is a circular orbit, right? Different between them, the circle has a one center right here, and the radius is same everywhere. But the ellipse has different radiuses. It has one direction larger radius, other direction is smaller one called the major axis. The other one is called the minor axis, then which is the smaller one, right? So then the ellipse, the shape of the ellipse is actually basically can understand by looking the parameter of the whole eccentricity E. E is actually just square root 1 minus b square over a square. Then if I know the b and a, then we can calculate the E, right? So the E usually in between 0 and 1 for all these bound orbit. Bound orbit means the orbital energy is actually negative, which is bound to the center of that orbit automatically, right? So in such scenario, usually this E is actually in between 0 and 1 for all the bound orbits. So which means depending on that parameter, we can actually understand whether ellipse is actually very uh, distorted one or very close to the circular orbit. Now you can see E0 is the circle, obviously, because A and B is same. Then E is 1 is actually almost like a parabola. So then the E is like 0.08 is actually this purple line right here, which is a nice ellipse. So the depending on that E parameter, we can understand how this actually this ellipse is actually whether it really distorted or not. And the ellipse has two focus point. The circle has only one center. Center is actually the focus point itself, but the ellipse has a center itself and the two different focus point. So that's the idea, which mean when the planet is actually orbiting on the elliptical path, the sun can be on one focus, then the planet is actually orbiting around that. Then the ellipse has various other the important parameters. Vertex point is actually when this cross the major axis right here, then the core vortex is actually minor axis crossing right there. And then the Earth orbit, on the other hand, is actually very close to the circle, because if I calculate the Earth eccentricity, that number is about almost 0.01, because this number is almost very approximately we can consider zero. So which means for our calculation in this class level, we're going to treat the Earth orbit as a circle, and then we do all the calculation with the circular orbit, but it is not technically perfect circle, it's slightly elongated. Okay, and when the Earth is actually orbiting around the sun, then the closest point to the sun is actually called the perihelion, which happening around like June 2, and the furthest point is actually the aphelion, which actually happening somewhere like July 2. And then in between these two radiuses, actually, if you calculate relative to the sun center, this is almost very same. This is the same idea which can understand by looking into the planetary motion, and the satellite motion around the Earth, and then so on. So our calculation is solely then based on this E close to zero scenario, right, in this particular class. But in real calculation, somebody sending the rocket to the moon or something, then they have to consider that and then do the calculation with up to about like 8 decimal place or 10 decimal place accuracy, right? So that's a different. So then the law number 2 states that this satellite orbiting, when it orbit, it actually sweeping out same cross-section area within the same time period. So A to B, let's consider delta t time period, and then the C to D consider delta t time period, then E to F consider delta t time period. Within the same time period, all of these cross-section areas A1, A2, and A3 are actually the same. Why is this happening? Because of one simple condition. So when the planet is orbiting around the sun, or any planet is orbiting around any focus point, sun is on one focus point right here. So one thing on the circular path is stay constant. That is actually angular momentum. If you remember the angular momentum is actually r cross the linear momentum. And linear momentum, on the other hand, we know mass times the velocity. This is going to be mass times r cross the velocity of the object, right? So the velocity of the object, we can understand, maybe depending on this radius direction, it's not going to be now 90 degree, right? If I draw this line, you can see, unlike the circle, this velocity is actually along this tangent line at that particular point, but that is not 90 degree exactly to this radius. So we can separate them out. One 90 degree velocity component, one is actually along the radial direction. Now, along the radial direction component does not participate because it is a cross product. Only this tangent velocity component which going to actually participate. I'm going to mark that line right here is actually the perpendicular component. Two lines right here is the parallel component. Then right here, only the perpendicular component is actually participating to the angular momentum. Then we can understand the separation between angle between the R and V is 90 degree. Then this is going to be R times mass times RV, and in the direction we can say in head. Now, if you look at it here, mass of the planet is actually remaining constant. What changing is actually R and V. So if I consider, let's consider the angular momentum at point A and angular momentum at point E. These two places, since it is along that part, circular orbit, there's no any external torque acting during that A to E motion, these two angular momentum should stay exactly at the same. So should this stay exactly at the same means, we can easily understand R1, V1 at point A should be equal R2, V2 at point B. What does that mean? V1 is equal R2 over R1 times V2. Then obviously you can see this is the R2 and then this is the R1. R1 is obviously less than R2. What does that mean? R1 less than R2 means V1 is actually much larger than V2. When it is closer to the sun, it's moving faster, right here. When it is further away from the sun, it actually moving slower. So that's the idea. So its angular velocity automatically adjusting, but amount of cross-section area always remaining the constant. So that's the idea. Okay, so that's the law number 2. Then the law number 3 is we already discussed. That means if I consider the satellite motion is actually almost closer to the perfect circle, then it has a tangent velocity v, radius r. This is going to be the sun center. This is going to be mass of the sun. This is going to be the mass of the earth, for example. Then this should have attractive force, two of them always. That attractive force, we know I can write GMS, GME divide by radius between sun and earth to the power 2. That should be equal mass of the earth and then tangent velocity to the power 2 divided by radius of sun and earth. Now mass of the earth cancels out, one of the radius cancels out, then we know velocity of the earth, which I can rewrite 2 pi r of AC divided by the period around the earth on earth orbit, which is about 365, right? 365 days multiplied by 24 multiplied by 60 multiplied by another 60 in unit second. Then which mean again I can actually simply derive the formula which I got earlier, right? So in this case you will get t to the power 2, which is equal 4 times pi square divided by gm r to the power cube. So which means t to the power 2 is directly proportional r to the power cube. That is the law number 3. Obviously that's why earlier I mentioned we derived that law very earlier in this today's lesson. And then that is the Keppler law number 3, which we can understand very easily by applying to various different observations. If we know one thing, we can actually estimate the other parameter and then so on. Okay, so that's the idea. Then at very last, we're not going to go very in detail in this calculation, but it's something very useful because for example, we know the tidal forces, tidal waves, right? So the depending on the time, then the earth waves come further towards the shore, and then sometime it actually stay away from the shore. So that called the tidal waves. The tidal waves happen because of the tidal forces. Tidal forces actually can be understood only by using this universal law of gravitation, the force between the moon and earth. Then again, moon moving through little bit elliptical path, which means sometime it's going to be closer to the earth, sometime a little bit further away. As a result of that, the z, the waves is actually dragging one way or the other. So as a result of that, it can produce the tidal waves. And then very last is actually the idea of the extension this idea into the next level. That is what actually the Einstein did early 1900. So he first asked one question. That question is that what happens if an object velocity becomes very, very fast? So that's the idea of this speed of the light. So what happens if something moving very close to the speed of the light? Then all the things actually gonna change. That where he actually generate his famous idea of his special version of relativity, the famous equation which comes out. There are three important results come out from that. One of the equation actually, E is equal mc squared, which is mass and energy is not the two things. It actually the same thing. You can write the mass is energy divided by light speed to the power 2, which means mass and energy is the same thing. And the other one is that if something moving really close to the speed of the light, so the time is actually delayed and the length is contracted. We will study all of those things in PHY 291 class. If you're interested doing it it next semester or maybe following semester. And the other important results which Einstein produced is actually what we nowadays call the curvature of space-time, which means space and time is actually not two different things. It actually the same thing. It actually work together. It happens together. So the idea is that this moving object around one object, like for example the circular motion, we explain by using this idea of centripetal force and then things like that. But in really that because of geometric curvature of space and time, not just because of anything else. So that's the idea which Einstein put forward in 1915 in his famous general version of relativity, which is considered the most um, most unique idea which one human being produced, I think, for over the all history in any sciences, really, because that's the only theory which can explain most of the ideas of our universe, how the universe works, things like that. So we will stop from here. So